four particularly promising and exciting areas for the future. One is improved materials for improving conversion efficiency by as much as a factor of 2. The second is luminescent concentrators, meaning optical devices that can take solar light and change the spectrum and concentrate it in a rather novel way that I'll illustrate in a moment. Third is the antenna method. I've been speaking of solar cells, but your cell phone and your radio and your television convert electromagnetic radiation, which is just light at a different wavelength, into electricity quite effectively with the simple antenna effect that we're all taught about in high school or first-year university physics. Why not do that with sunlight? Now, no one knows how to do that yet, but I'll describe in a moment why this poses a tantalizing prospect and wonderful challenge. The fourth area is biological area. Can one convert sunlight via photosynthesis in a method which is prodigiously superior to the efficiencies that nature generates in natural ponds or outdoor conditions today? And I believe the answer is yes, and there's a good basis for it. So I'll take them one at a time. First, the semiconductor materials for solar cells. So the first area of materials for the solar cells is, and this is the transition from the earlier discussion we had, can we find materials that are better suited to the solar spectrum, interface to each other in a more efficient way, and therefore can boost the efficiency in a significant fashion. At least a factor of 1.5 I think is realistic in the coming decade, and the factor of 2 may be unrealistic, but it's theoretically possible, even more than a factor of 2. So that's in terms of the materials. The luminescent concentrator, the antennas, and the biological mechanism are more futuristic. There is some research, but they're in their infancy, and the performance is highly unsatisfying. But you asked a very good question about fundamental limits. The fundamental limits tell you it's possible. No law of physics precludes it. Therefore, it poses a wonderfully appealing challenge to physicists. The concept of a luminescent concentrator is to have a totally stationary device which can take sunlight and tailor it in 2 ways. Tailor the spectrum to the solar cells and increase the concentration. So again, we can benefit from very little solar cell and a great deal of optics. This is just a schematic diagram to illustrate it. This is a system which would not have to track the sun. What I didn't mention before, and perhaps I should have, is all of these concentrator systems must track the sun with accurate systems. They must be pointing at the sun at all times. That is an existing off-the-shelf technology, and it may only comprise about 10% of the system cost, but it still is not negligible. Here, you would have a slab of glass or acrylic or some other nominally transparent material in which there are dye-molecules or quantum dots, which are a new kind of technology that manipulate light from one color to another, which would absorb the solar spectrum, re-emit it at a different wavelength, better suited to the solar cell performance, and then by total internal reflection, the same thing that happens in an optical fiber or to a limited extent in prisms, brings that light, after a small amount of leakage back out the entrance, to the sides which we would cover with solar cells. It would be a stationary concentrator of immense potential. And the laws of physics allow it. The problem is, what are the materials that we dope this transparent acrylic or glass with? No one has answers for that is satisfactory. The answers to date are extremely inefficient. The appeal is it can be quite low cost, totally stationary, and the concentration can be tailored to any level you want, even greater than the 46,000 I mentioned before in principle, because that's based on geometric limits, and here we have what's called brightness enhancement. We manipulate the spectrum, not the geometry. It's a complementary physics that's fascinating. The third level is the antenna effect. Can we have an analog? Can you take your cell phone and just scale it down so it would work for sunlight? Now the answer seems to be, in principle, yes. The laws of physics allow it. No one knows how to do this yet. But the fact that the laws of physics allow it prompts us to start the investigation. This is the latest state-of-the-art for far infrared radiation. This is taking electromagnetic radiation, what we call light, which is lower in wavelength than the microwave that powers your cell phone, and is converting it into electricity. For those who understand the dimensions, the wavelength of this is about 20 micrometers. Remember that your cell phone is dealing with centimeter wavelengths, several centimeters. This is at the level of tens of micrometers, so it's orders of magnitude less. And already there's progress. This is an array of antennas for infrared radiation. It's extremely inefficient, unfortunately, but the very fact that it does convert infrared radiation into electricity and can rectify it, meaning it can give you a DC electrical output, is a major breakthrough. This has been done at the Stanford University and some private companies in the US. I find this a wonderfully encouraging indication that we should be able to apply our knowledge of optics and of materials, and nanofabrication is absolutely essential here because the antennas will have to be hundreds of nanometers. That synthesis awaits to be solved, but I believe it comprises a very exciting potential development for future solar technology. And the last one relates to algae. Algae are single-celled organisms that photosynthesize. Unlike plants, they don't have to grow roots, they don't have to grow leaves. Therefore, they can focus more of their resources on photosynthesizing efficiently. Indeed, they are the most efficient photosynthetic organisms known on Earth. Now, you asked about fundamental limits. That was an excellent question. And there is a fundamental conversion limit for algae from sunlight plus water plus carbon dioxide into sugar. This is the chemical storage of sunlight. It's a dream, because then from sugar you can produce fuel and drive your car around on that, or your airplane, or any kind of automotive vehicle. Well, the problem is that algae in nature are order of magnitude below that fundamental limit. So there's a question: does that mean that no human intervention could come up with clever optics, clever genetic engineering, clever reactor design? After all, we can build reactors and expose the algae to light in a particular temporal, that is time-dependent fashion, spatial pattern, intensity. We can manipulate the colors. Well, some of the research we did during the last few years indicates that the answer is yes. It is possible. These limits could be realized. If it were easy, it would have been done, of course. So this prompts the beginning of a research direction in biotechnology, the ultra-efficient conversion of sunlight into biofuel. Not via corn and sugar and palm oil, which is intrinsically limited to levels which are really too low to be sustainable for the world, but algae have that latent capability built in. So that fourth area I find of futuristic research is what I'd call solar biology. Tweaking photosynthesis to get the most out of organisms that nature doesn't execute intrinsically, but we as scientists can. How can photosynthesis be manipulated? There are ways to do it. One of the more intriguing ways is synchronizing light input to it. You don't just irradiate it in a continuous fashion. These are possibilities, and they hold enormous potential. And I think the solar biology is the key answer to solar fuels. Solar electricity produces electricity. Storing electricity is problematic. It can be done. It's expensive. It's short lifetime, but it doesn't give you fuels. This gives you fuels. Just like sugar and corn biofuels give you fuels, but that's not really a sustainable solution, and that's clearly understood. In this direction, the laws of nature tell you it's possible, and it can be sustainable and will be order of magnitude more efficient. So I say, let's embark in that direction. And the nice thing here is it's almost a zero carbon dioxide balance, because the algae need CO2 to photosynthesize. Then you convert them into biofuel. When you combust it in your engine, you produce CO2, and it's almost neutral, as opposed to biofuels from corn or sugar, where it's far from neutral. there really isn't that much advantage. The only advantage there is you gain energy independence. You don't have to import your oil or drill into the ground. You can grow it. But there are all kinds of I think well-articulated drawbacks to growing crops like corn and sugar instead of other foods. In algae, one of the advantages is all it needs is saline water, sunlight, and carbon dioxide. Nothing else. It doesn't need fertile land. Deserts are great places to breed algae. So we need optics, we need biotechnology, we need some genetic engineering, we need clever material science. So I say let's embark on it. And we have started on it, but this is a long path. The major advantage of the concentrated photovoltaics is it's far more efficient. It's more than a factor of 2. More than twice as efficient as the best solar thermal. This is huge by any technological criterion. That said, its drawback is storing energy. Electricity can be stored, but it's both highly expensive and short lifetime. Like the laptop you hold in your hand, that battery is expensive and it only endures for about 1,000 cycles. This is not the sustainable technology. There will be progress, and perhaps within a reasonable period of time, there will be viable solutions, but it's not available today. So, when one of these systems encounters a cloud covering the sun or a rainy day, it generates zero power. Not low power output, zero power, because concentrated sunlight, because diffuse sunlight cannot be concentrated. Utilities despise intermittent input. They don't want 100 megawatts, which they're pleased about, and then within a few minutes it drops to zero. That's the drawback of photovoltaics today. As long as it doesn't penetrate the grid in terms of a high percentage, they tolerate it. That's photovoltaics. Its advantages and disadvantages. Solar thermal, the disadvantage is it's less than half the efficiency. Its big advantage is the potential to provide reliable, continuous power. And the reason is twofold. There are two options in solar thermal for continuous operation. The simple one, the off-the-shelf one, is you take a line of natural gas, and the steam turbine that's being fed by solar has two inputs from the solar field and just burning natural gas. So whatever solar does not provide, let's say you have a 100 megawatt turbine, if solar provides 80 megawatts, you burn gas to provide the other 20. The turbine sees it as a black box. I just need 100 megawatts of power. I don't care where it comes from. You could burn gas for 100 megawatts of power too. This is very attractive to utilities. The other option is to store heat. You can oversize a solar system. Part of it drives a turbine. The other part charges a high temperature thermal storage facility like molten salt. And then you don't need the gas. If there's a cloud, then the thermal storage facility is drained, or part of it is drained, and the heat drives the turbine. So again, the utility sees an uninterrupted source of electricity, and they love that. This is the trade-off. I don't think that any one technology will conquer the field. I call this the multivitamin approach. Just like you don't take just vitamin D, you take A and B12. So it will be with solar. Each of these technologies will have a niche. They will all be adopted. They should all be pursued. And they all have a role. Whatever